Good morning, everyone. I'm Kaiwei. And so today I will talk about how can we use just a small amount of cross-tier mirroring to achieve efficient load balancing in a tier storage system. This is a joint work between Madison and Google. So emerging new storage devices, such as low latency SSD, are filling up the performance gap within the traditional hierarchy. So if you think about a modern hierarchy composed of a low latency SSD and a flash SSD, and on the devices we tested, the maximum read bandwidth of low latency SSD can be lower than the flash SSD on the larger requests, and slightly better than the flash SSD on the small requests. So this aligns with the finding in previous work that the modern storage hierarchy is become less hierarchical. So if we regard the low latency SSD as a performance tier and flash SSD as a capacity tier, traditional approach will place the hard data on the performance tier and cold data on the capacity tier. Suppose we assume roughly 90% of the requests go to the hard data and only 10% of the requests go to cold data. And so what will happen is that when the workload becomes intensive, the performance tier will be saturated, but capacity is merely used because majority of the requests were sent to the performance tier. So this example reveals a fundamental problem of a traditional approach is that the capacity tier performance is severely underutilized. So previous work has addressed this problem in tiered memory system by using migration, such as Cloyd and Batman. So the idea behind this system is simple. So when the workload becomes intensive, this system will move some of the hard data from the performance tier down to the capacity tier. So some requests can be served by the capacity tier. So as a result, the system will deliver higher throughput because of the extra bandwidth from the capacity tier. So however, migration is expensive in the storage hierarchy and has three major drawbacks. So first, during the migration, the background traffic will compete with the application for the bandwidth on performance tier, and therefore reduce application performance. And second, migration-based system is hard to adapt to bursty workload because storage tier are large, but the bandwidth is limited. So moving hundreds of gigabytes of data can take tens of minutes or even longer. So third, migration will trigger extra writes in the background, which will consume the device endurance and therefore reduce the device lifetime in the long term. So we asked, can we achieve load balancing without paying the high cost of migration? And to address this question, we propose mirror optimized storage tiering, or MOST. And the key idea of MOST is simple but efficient, cross-tier mirroring some data in a tier system. And this is based on two insights. First, we observe traditional tier system only maintain one copy for each data, and therefore migration is the only way we can adjust the load distribution between tiers. So by introducing the mirroring in the traditional tier system provides the opportunity of routing-based balancing, as shown in the right diagram, where the request sent to the mirror data will go through a loss switch that can offload requests down to the capacity tier without any migration when the performance tier is saturated. Second, we observe that the access pattern is naturally skewed, and therefore only a small amount of hard data is enough to make a majority of the requests routable. So as a result, through our evaluation, we observe most can achieve up to 2.3 times higher throughput and reduce device write by 84% on a range of static and dynamic workloads. So the rest of talk is organized as following. First, I will detail the design of MOST, start with the data layout, and then I will talk about how we balance read and write traffic. And at last, I will talk about how read-write balancing interact with each other. So let's start with how the data is laid out in the MOST system. So MOST classifies data into three categories. So the hardest data is mirrored, and the warm data is placed on the performance tier, and cold data is placed on the capacity tier. And we use similar hardness tracking as previous system in which we maintain read-write counter for each block and periodically halve them to keep freshness. So by using the hardness information, we are able to know the hardest data in the system and mirror them across tier. So I will then show you how to use this small amount of mirror data to achieve fast load balancing for read. So we introduce a component called loss switch, which is responsible for distributing the traffic across two tiers. And the behavior of this loss switch is defined by a variable called offload ratio, and which is X here. So when a request goes through the loss switch, X percentage of traffic is offloaded, to the compass tier, while the remaining traffic is sent to the performance tier. And since the optimal data offload ratio is not static across the workloads, so most have another component named optimizer, which dynamically tune the offload ratio based on the system status. So this optimizer requires no prior knowledge of the workloads or devices, but uses a simple yet efficient feedback-driven dynamic algorithm based on the request latency. So for example, if the performance tier is saturated due to intensive workloads, and the latency of the performance tier will surpass those of the compass tier because of the request queuing, and then most will increase the X here, which is the offload ratio, thus increase the amount of traffic offload to the compass tier until the latency of accessing two tiers are equalized. And when the workload becomes light, most will bring the traffic back to the performance tier because it has lower latency by adjusting a routing variable inside log switch. And therefore, with this design, most can route traffic based on device status without triggering the migration. And when design most, we not only want to balance read, we also want to balance writes. And a naive way to handle write is write through, where a write request will update 2 copies of data. However, write through is expensive. Since we're updating both copies at the same time, the system performance will be bottlenecked by the slower devices. And so, therefore, most send write to only one of the copies. So just as we did with read. So each incoming write will go through the same log switch as read and controlled by the same log offload variable X. But unlike read, write to one copy will invalidate another copy. And therefore, another copy will be invalidated. So write invalidation will disable rebalancing for the same data because all the subsequential read can only be sent to the valid copy. So if you see the bottom diagram, one of the copy is invalidated, and all the next read can only be sent to the valid copy. So if one of the copies, therefore in the long term, the system will gradually lose the ability to balance read. And let's see how most address this problem on 2 different scenarios. First, the data is read heavy, where write happens rarely, and therefore most will remirror this data in the background with reasonable cost in order to restore the read balancing ability in the long term. And second, the data is write heavy, so which means that data will be updated frequently. And on this scenario, we don't need to remirror data because the write itself acts as a load balancer. For example, if we see the write diagram, if the perform tier gets saturated, and we want to offload traffic to the compass tier, and we can just route the next write back to compass tier, and therefore the hop sequence request can be served from there. So we observe that this write invalidation will also interact with write itself. So if the write is a full write, and which overwrites entire blocks, then the next write to the same block can be sent to any of the copy without any issue. So in this case, the write can be balanced just as read. However, if the write is a partial write, which only updates part of the data block, then this partial write can only be sent to the valid copy. Otherwise, we will have valid data on 2 devices, which breaks the consistency. And therefore, we want to write to be full write instead of the partial writes. And so how do we avoid partial writes? We first observe that application I/O naturally aligns to device granularity, for example, for 4 kilobytes. And to avoid partial writes, we need to manage every block in 4 kilobytes. And therefore, every write is a full write. But it turns out to be very expensive to manage every block in 4 kilobytes because we need metadata to keep track of block position in the hierarchy and also status to keep track of hotness and mutex to ensure concurrency control. To maintain this information, we need around 13 gig metadata for a 2 terabyte hierarchy. And therefore, we need to manage the hierarchy in larger granularity. So most use 2 megabyte as trade-off for smaller metadata. But managing metadata in 2 megabyte will make every 4 KB write to the mirror data become a partial write. So to address the issue, we break the large chunk of the 2 megabyte block into 4 kilobyte subpage for the mirror data. And therefore, these subpages can be write independently. And to save metadata, these subpages are matched both logically and physically together with shared metadata, include physical address, mutex, and hotness tracking stats. Because of these pages are writing separately, and therefore they could be placed differently across the tier. So we use 2 extra bits per page to keep track of their position. So the right diagram, we can see 3 pages with different status. Sub page 1 is clean with 2 copies. And sub page 2 is dirty with one valid copy on the perform tier. And sub page 3 is dirty with valid page on the compass tier. So by doing so, we have 2 benefits. So first, 4 KB requests become override to each sub page, and therefore avoid the partial write problem we have mentioned before. Second, we save metadata because the majority of the block is managed in 2 megabytes, while only a small amount of mirror block needs extra bits to keep track of sub-page placements. So as a result, most only need 140 megabyte metadata for a 2 terabyte hierarchy, in compared to 13 gigabyte, we manage every page in 4 kilobytes. So then, I will show you how we implement most and evaluate against state-of-the-art approach. So we implement most Madison open source flash cache engine inside CacheLib. So CacheLib can manage multiple storage devices as flash cache, and it has user-level storage management layer that manages multiple devices transparently as a single large storage devices. And inside this storage management layer, we build Cerberus and our implementation of most. And beside Cerberus, we have 5 other counterpart systems. So first, strapping, which is the default method in CacheLib to manage more than 1 devices. And also 3 other counterpart systems, which is tiering-based, HEMAM. So it's a classical tiering system which migrates hard data into the perform tier periodically. And Batman and Cloyd, which are both state-of-the-art tiering systems which use migration to balancing the load across the tier. And it will also implement the state-of-the-art caching system, orders, so which offload cache hit to the compass tier when the perform device is saturated. So in the following experiment, we use 2 devices, one Optane SSD as the perform tier, and one Samsung Flash SSD on the compass tier. So we first see a dynamic read-only workload with a 2-minute burst every 15 minutes. So we first show how classical tiering systems react on such workloads. If we look at the top graph, we can see that HEMAM, the classical tiering system, do not do any load balancing when the load bursts, and therefore the throughput is far below the best throughput we can get from both devices. And because of no load balancing. And then we look at Cloyd, which is the tiering system with migration ability. So, which is the black line in the graph. We can observe from top graph that its performance even worse than classical tiering approach with no balancing. And the reason is migration, which is shown in the bottom graph. And during the loud burst, we can see a burst of demotion traffic in the Cloyd that are trying to migrate block down to the capacitor. And during this period of time, because of this migration traffic, the application performance will decrease. And after loud burst ends, and because the Cloyd has already migrated some data down to the capacitor, it needs to migrate the data back to the performance tier in order to get performance from the low latency performance of the performance tier. And in the bottom graph, we can see the performance traffic show up. And in total, Cloyd migrated 400 gig data during the whole process and result in 26% lower throughput than HEMAM, which is the approach with no balancing. So let's see how Cerberus behaves on such dynamic workloads. Cerberus is shown in the orange line. So in the top graph, we can see that at low burst, Cerberus achieves 1.5 times higher throughput and be able to use the bandwidth from both devices and therefore achieve the best throughput. And Cerberus achieves this efficient load balancing by routing the traffic across the tier during the load burst and without triggering the migration. And as a result, Cerberus achieves 45% higher throughput compared to Cloyd, the migration-based approach. And what about writes? So we also have experiments for the write-only workloads. And we observe similar behavior of these 3 systems and see a 27% higher throughput from Cerberus compared to the Cloyd. And in the paper, we also have rewrite mix workload. And beside these dynamic workloads, we also have experiments. Cerberus improve workloads across different intensity. And we also run Cerberus inside an end-to-end experiment with cache bench, which is a local-side cache benchmark, and with different value size and write ratio, and also for production workloads. And Cerberus also improve YCSP workloads. And then we come to the conclusion. So for the conclusion, we review the problem of migration-based load balancing in tier storage, and we propose mirror optimized storage tiering, which cross-tier mirror some small amount of hot data to achieve efficient load balancing. And we believe as the storage tier becomes less hierarchical, such hybrid storage system may offer further benefits. And thank you.